Okay, so this is a slightly modified version of the first slide which we put up in the fourth lecture. These topics on the left, which are in a fainter font, are topics we talked about. And I would like to continue with that theme because it will give us some insight into Huygens principle. Okay. Huygens principle is usually taught at a fairly early stage, that's standard, but it's an ad hoc principle. It's not justified. It's justified by the results that it explains. And that is exactly how it happened historically. It was justified by the results. But we are now taking the point of view that we understand plane waves, we understand superpositions of plane waves, either one or two or a large number to form wave packets. And one of my main goals today is to see that we can use these wave packets and the way that they behave to understand Huygens principle. So that would kind of complete your understanding of wave optics in that sense. And of course, you would naturally want to apply this. Okay, and I'll tell you what I mean by zero slits and half a slit. But to start with, I'm going to have a fairly extensive recap of wave packets. Okay, and in fact, maybe even a few more remarks for which there was no time last time. So let's start with purely as a function of time. You have two frequencies. You have seen this before. The average frequency is omega 0, and the separation of the two frequencies is twice delta omega. Okay, and purely as a piece of mathematics, you can separate it into the center frequency minus I omega 0 t, and of course, electric field being a real quantity in wave optics, we would take the real part at the end. And then in the brackets, we have two terms corresponding to the two waves. And when you add them up, they become cos of delta omega t. Now remember, delta omega is supposed to be small, omega 0 is supposed to be large. So this is rapid oscillations, and this is a slow modulation. Okay. So that's what it looks like. The omega 0 real part, rapid oscillations, and the red line is the slow modulation. Now, even at this stage, there is a clarification which I have to make. Delta omega here is half the frequency separation. Okay, we are normally taught that the frequency of beats when you have two sound waves is the difference in the two frequencies. So that's a point which I have to clarify. And the reason is that when you listen to beats, you're actually detecting the square of this quantity. You're detecting the intensity. Okay, so when you square this, the phasor diagrams we need not go through. So strictly speaking, if you could detect that change in sign, then the modulation would return to its original value when delta omega into some capital T is 2 pi. So this would be the periodic time, the period between two successive return of the modulation, that red curve, back to the same value, magnitude and sign. But if you look at the average intensity, we have to square that. And if you square delta omega t, the cosine, you will get this quantity. And now you see that we get a constant term, an average, and double the frequency. So now the period is given by 2 pi divided by this quantity, twice. Okay, sorry, there's a typo here. This should be delta omega. Okay. So 2 pi by twice delta omega. And twice delta omega is the frequency separation. So that's why the usual rule that we learned that omega 1 and omega 2 give a beat frequency of omega 1 minus omega 2 is justified. Okay. Now, I mean, this is just to visualize things. Okay. If you have these two waves traveling in the same direction with slightly different wavelengths, which means slightly different frequencies, let us say they agree in phase at this point, but you notice have superposed two grids of parallel lines with slightly different spacing. So already when they're aligned here, they're not aligned here. The separation becomes still more as you move away on this side. And then if you have two numbers, you'll have something like an LCM. So after the LCM, they again coincide, except that you would have some integer number of one of the waves and n minus 1 or n plus 1 of the other wave. So we'll be using diagrams like this. And the next step we took was to superpose a continuous range of frequencies going from minus delta omega to plus delta omega. So you've seen this before, and you can do the integral. That's the most straightforward thing. And this again is the rapidly varying frequency, carrier frequency, if you like, or center frequency. And this is the slowly varying term, which is of the form sin x by x. And here is so the red curve is now sin x by x. Unlike in the previous case, it never returns to its original value. In fact, it gets damped. So we have succeeded in creating a wave packet, something of more or less limited duration pulse. Okay? And the reason why it doesn't return is that now we have an infinite number of frequencies. Okay. For example, if you have two frequencies separated by a very small range difference, you have to wait a very long time before they come into phase again. Okay. And in the limit of an infinite number, okay, it never recurs. Okay. You never get back to the original. So, I mean, this is just a simple illustration of this point, time equal to 0. If you put t equal to 0 here, this becomes 1. So that means all the terms in this integral are adding up in phase. You can either add them up, keeping a common point for all the vectors, or you can put the vectors head to tail, and that's what's happening at t equal to 0. And the next value of t I have chosen is somewhere here. That's when this function becomes 0, right? Sine of pi is 0, right? So if t is 2 pi by delta omega, you're sitting somewhere here. Now, of course, the individual terms in this integral do not vanish, okay? But they are out of phase, right? Because you have a finite value of t, and the way that they vanish is that they point in all possible directions, okay? By the time you go from minus delta omega to plus delta omega, the phase changes by 2 pi. So all the arrows are pointing in all possible directions, and they add up to 0. And if you believe in the head-to-tail construction, this is what happens. Okay. So I'm sorry, this is just a recap, and again we will use this pictorial way of understanding what happens when you superpose a continuous range of frequencies. Except my drawing abilities being limited, I have drawn only 5. So all 5 are in phase here. You can see they are getting out of phase as you go away. And by the time you move to that point, if you are sitting somewhere here, all of the 5 waves have completely different phases and they cancel. So this is the temporal wave pattern. One thing which I encountered between last lecture and this lecture is the original figure drawn by Young when he had to explain his work to the Royal Society in 1803. What a marvelous figure. It should really be present in all our textbooks, right? Of course, some version of it is. It also gives an idea of his way of thinking, right? So he simply thought of the two slits as two sources. He didn't worry about diffraction by this slit and so on. These two sources give out spherical waves. And you see, even without any calculation, that naturally these dark lines appear, which are where the two waves are out of phase, because you can see that. And then you have these lighter regions. And of course, this also is a place where the two waves are in phase. Here also they're in phase. So the appearance of the fringes, and also the fact that the fringes fill space, beautifully brought out in this picture. And what I showed you in the previous lecture, and I'll show you again, is just what is happening near the screen. Now, near the screen, each of these spherical waves or circular waves can be thought of as a plane wave. And then you have this grid of two plane waves, which we called a Moire pattern. Right? So again, I'll go through this very quickly because it's just a recap. Right? We had two wave vectors. I have chosen them to be perpendicular to these two grids, two waves. Right? They have a common value of kx, but ky, which is 0, and ky has two opposite values. And just as we had omega1 minus omega2, we'll have k1 minus k2. And just a warning, these are k vectors. So the algebra is pretty much the same. You add up these two waves. And now, of course, you are looking at how the phase varies in space. So you do the same kind of factorization. And then you say, this k1 plus k2 is large. And remember the inverse relationship of k to wavelength. So this means this is a wave of short wavelength, which is being modulated by a cosine function of a much longer wavelength, because k1 minus k2 is small. So what I didn't write out last time is I didn't explicitly write out k1 and k2, which I've done now. So if this angle is alpha, alpha is half the angle between these two. So you have this angle theta here, and alpha is half of that. So k1 has a positive value of the y component, and k2 has a negative value of the y component, and of course the x component is the same, like it. So again, the same clarification, that if you are only looking at the square of this, the intensity, then the periodicity will not be k1 minus k2 by 2, it will be k1 minus k2, because you're taking cos square, and cos square theta has a term which is cos of twice the angle. So this is the periodicity of the intensity. It's k1 minus k2. And what is k1 minus k2? I've written out the two vectors here. So subtract 0x component, and 2k sine alpha is the wave vector, which is now purely pointing along y. And that agrees with what we are seeing in this picture, that if you're looking at the modulation, this dark and dark and light pattern, that is like a wave which is going purely in the y direction, right? And its periodicity is given by 2 pi divided by this k vector. And this agrees with what you would calculate in the normal Young's experiment. But please remember that I only told you the situation near the screen. And now we would like to know what happens to the spatial wave packet as you look at it in space, right? Not just on one screen, but how does it evolve? So we have, so the situation that we saw so far is the situation on this plane, okay? And on this plane, you find that you get the maximum intensity here, and as you go away, it falls off. Now, why should things be different on any other plane? And that is because of kx. Okay? And the important point is, in the case of when we were interfering just two beams, they all had the same value of kx. But if you go back, you will see. Sorry, and we go forward. Yeah, these are just two beams. But if we had had a full range, these points would have been on a circle, and you would not have had the same value of kx. Okay. So, of course, the magnitude of the k vector is related to the wavelength, and we are still being monochromatic. So only one value of wavelength, that is k 2 pi by k. So kx squared is k squared minus ky squared, right? And that's going to be different for the different values of ky. Now, we didn't worry about that at x equal to 0 because kx was irrelevant. But these waves, even if you move along the x-axis, okay, at y equal to 0, these different waves propagating in different directions will start to get out of phase, even though they were in phase here. Now, so let me explain that. And this gives us a little more insight or intuition into what this vector k is. Of course, we defined it as 2 pi by lambda into a unit vector pointing perpendicular to the wavefronts. That's how we defined it in the fourth lecture. But so here is lambda, and suppose one wants. So let us say this is a wave traveling at some angle theta, but we want to move along the x-axis. What is the periodicity which we will see? Well, this is actually longer than this, right? It's lambda divided by cos theta. So that if you multiply by cos theta, you get back to lambda. Equally, if you move along the y-axis, the periodicity is lambda divided by sin theta. Okay. So clearly, you can't make lambda into a vector because the distance that you have to travel to get back to the same value of phase is actually increasing. On the other hand, this itself tells you what you should do. You should take something which is the reciprocal. So if you instead talk of phase change per unit length, that is our definition of K, then in this direction, it's 2 pi by lambda. In this direction, it's 2 pi by lambda into cos theta, right? The phase change per unit length is actually less, and likewise in this direction. So this simple. And for our problem, we are now superposing waves which are going to have different values of theta. So therefore, as you move along x, they will get out of phase. That's the point. So what I have done, I think, in the next figure is to make a more elaborate sketch of, I think I have maybe 9 waves or something here. The central one is propagating exactly along the x-axis, and the other ones are pointing with various values of ky. And they are all in phase here. And given what I have just told you, you can see that they have started getting out of phase. You can see this. There's this spread here, bigger spread here, bigger spread here, bigger. So we had a wave packet which had some limited size here. And it was more or less a plane wave, right? But what seems to be happening as you go further and further away is, number one, the intensity is decreasing because these are getting out of phase, even along the x-axis. And if you just look at the places where these waves are in phase, which show up as dark lines, right? Because the way I created this figure is to use a PNG file. In a PNG file, every line can have a transparency. So if you superpose 2 lines, it gets darker. Now you can see that you are actually getting spherical waves, right? So it's as if you had a wave packet of very limited extent on the plane x equal to 0, and as this combination of waves propagated, they kind of spread out, and effectively they seem to be combining to get a spherical wave. By the way, if you phase conjugate and go backwards, again you see a spherical wave. That's not surprising. All right, but of course these are all pictures, and we have to do a little calculation. So here are all the k vectors which we are trying to superpose. Okay. And notice that they have a range of values of ky in some range, say minus alpha to plus alpha. Okay. And they have slightly different values of kx because of the curvature of this circle. So at x equal to 0, this is exactly identical to the calculation we did for a wave packet in time. Right? You get sine of alpha y by alpha y. I think I didn't put in a plot this time. It's basically a function which will fall off when y is of the order of, again, there's a misprint here, I'm sorry. It should be k alpha y, right? Because there's a k here, there should be a k here and a k here. Just shows how much you prepare. At least you do miss something. So it's sine of k alpha y by k alpha y. So when you can now find the width, when this quantity goes from minus pi to plus pi, so you'll get 2 pi by k alpha. This is also lambda by alpha. But all this is only when you stick to the plane x equal to 0. And this is something I've already told you, that if you have different values of theta, you'll have different values of kx. Now, of course, theta is small. We are in the paraxial regime, even still smaller. But this gets multiplied by x. So if you go far enough, it will give you appreciable phase changes, and that's exactly what we saw pictorially. So now I have to modify this integral, right? So it has the same thing, except now I have added a term kx times x. And what is kx? It's got a k factor, which is independent of theta. So I can pull it out of the integral, exponential ikx, right? And the factor that depends on theta, I have to keep inside the integral. So now we have a more complicated integral. Instead of just having k theta into y, we also have minus k theta squared by 2 into x. So what are we going to do about this integral, right? So before doing something, I will try and again give you a slightly modified version of this. And this is mathematically more convenient. It's also, interestingly, physically a little more realistic. If you look at the spatial distribution of the field in the plane x equal to 0, in the previous example, it was sine of k alpha y by k alpha y. So it's a kind of oscillating function. Of course, with a finite, with most of the energy was in a limited range. But very often, if you look at a laser beam, it actually seems to have a Gaussian shape. So Gaussian is, of course, this famous function. So now this is a slightly modified wave packet. And we're going to spend some time on it because this is the one where you will be able to make very explicit calculations for all values of x and y. And that is there in the problem sheet. In fact, it's already there in the problem sheet for lecture 4, but I was being very ambitious, right? So certainly it's the same problem sheet will enable you to convince yourselves of what I'm telling you in this lecture. So now, instead of having a function which is constant from minus alpha to plus alpha, that's what we had last time, we now have a function which has a maximum value at theta equal to 0. And then there is some quantity called sigma of theta. It is the qualitative meaning of this, it's a spread in theta. So if theta becomes much greater than this, say suppose theta becomes twice this, okay? So then you'll have a factor of 4, 4 by 2 is 2, exponential minus 2 is about 1 by 8. So the function has fallen off quite a bit. So the sigma theta is a measure of the spread of theta in the Gaussian. And then earlier we had a factor 1 over 2 alpha here. And now we have put some other factor. And the purpose of this factor is to ensure that even if we change the width, the total integral should be 1. Okay. So now I have not put in the x factor. So we are still looking at the electric field on the plane x equal to 0 as a function of y, because everything else is an integration variable or a constant. So the mathematical convenience is that this kind of integral involving a Gaussian gives back a Gaussian. And that is something which is explained a little more in the problem set. So the problem set is not just problems. There are some explanatory notes which will help you to understand how to do such integrals. Okay. So now we can ask, what is the spread in y? See, previously the spread in y was lambda divided by alpha, right? And because this is a Gaussian, if we bring this to the same form, exponential, we can identify what the spread is. So that's what I'm going to do. Just move this sigma theta squared k squared to the denominator. So it's y squared by 2 into something. And this something is obviously the spread in y. So the size of the wave packet in y at the plane x equal to 0 is 1 over k sigma, right? K sigma theta. So of course there are some extra factors of 2 pi, but apart from that, it's lambda divided by the spread in angle. So sigma theta is the spread in angle, and this quantity is really, we could call this whole quantity sigma y square, and you will get a similar uncertainty relation to what we got earlier. The reason why you have some discrepancy of these factors is because our definition of width is slightly changing from the previous wave packet to this wave packet. So don't worry about it at this point. Now, this is copied from the previous slide. Same thing. If you want to move from the plane x equal to 0 and move along the x-axis. By the way, this is what people call diffraction, right? You have some distribution of light on a plane x equal to 0. In this case, we created that distribution by superposing waves, but you could have created it by putting some screen also. Of course, to create a Gaussian, you'll have to put some kind of Gaussian screen, which transmits maximum in the center, and the transmission of the screen goes off. One can make such things, not difficult. So a real understanding of diffraction is going to happen when we go away from the plane x equal to 0. How do things spread out? And now, same integral, but now we have to add this added factor, k theta squared by 2. So the good news is that you people are going to study this integral in the problem session. This is certainly not the kind of thing which in a short lecture one will work out in detail, but I would still like to give you the basic concept. I mean, we've already seen the concept at a very qualitative level, that the wave initially seems to not spread and then it spreads out like a spherical wave. And for that, I'm going to give you a very simple-minded argument. Okay. So go back to 12th standard optics. If you have a slit of some width d, so d is like our sigma y now, then it would send light into some angles lambda by d. And in a way, we've already seen that. No? We have seen that the range of k values is k times alpha, where alpha is the range of angles, right? So that's the same thing. So suppose you accept this. It's a very simple-minded argument, but it gives us the essential point, and you will be verifying the details. Then now you have light beams propagating at different angles. So if they travel a distance x, they will spread out by x into the angle. Yeah. So x lambda by d. Now if x is very small, this is going to be small compared to d. Right? So d is some width like that. And for certain values of x, which are small enough, the width won't increase very much, right? Because this spread is going to be small compared to this spread. So up to a certain distance, you will get ray-like behavior, right? You will have illumination in a region of the same width t. But this cannot go on forever, right? This is what I told you. So long as x lambda by d is less than d, we can either say that the original plane wave is carrying on, but of course of width d. So what is the x up to which this can work? So just equate these two, or move this to the side. X has to be much less than d squared by lambda. So if you want a simple numerical example, you could have a laser of wavelength 1 micrometer, right? And let us say you have a slit of width 1 millimeter. Right? So d over lambda is a factor of 1000. So then you have to go to 1000 times d. You have to go to 1000 millimeters. So that means a laser beam of width 1 millimeter can be treated more or less as a parallel beam up to about 1 meter. And then it will start spreading out. And this also tells us how ray optics emerges from wave optics. Right? It can emerge provided you have beams which are reasonably large in size. If you try to push ray optics to the limit by restricting the beam by means of some hole or some slit or something like that, you squeeze it and then it starts to expand. Right? It starts to expand, and therefore this distance, if you keep decreasing d, then you find that sooner or later this is going to fail. Right? So this is also a criterion for the validity of ray optics in some sense. Now what happens in the opposite limit? X much greater than d squared. It means that the wave has spread out much more than the width of the original slit, and we have a spherical wave which subtends an angle lambda by d at the slit. And this is the case that you are taught in 12th standard. You put a screen really far off, and you find that you get a diffraction pattern whose angular spread is lambda by d. But what we have now learned from this argument is, if you bring the screen very close, then you will start seeing just the shadow of the slit. Okay? So now this is the argument which I have given you, as I said, somewhat simple-minded fashion. And to be fully convinced, you should take that Gaussian beam which I took, and there you can do everything quantitatively. You will see how the width increases. You will see how the plane wave becomes a spherical wave. And so therefore, it's a valuable exercise. So pictorially, if you have a beam which is restricted to some size d, never mind whether it's Gaussian or sinc or some other function, then there is a distance called Fresnel distance, which is what we worked out to be 1 meter in the case of a laser beam of width 1 millimeter and wavelength 1 micron, right? It's the Fresnel distance. And up to the Fresnel distance propagates more or less as a plane wave and then becomes a spherical wave beyond that. By the way, interesting application. I don't think I put a... okay. The interesting application is that people have used this to send laser beams to the moon. And the astronauts who went to the moon left some reflectors there. So you can measure the distance to the moon, and it is quite amazing. The distance is measured to an accuracy of millimeters, and they have been able to detect astronomical effects like the moon distance increasing by 4 centimeters per year. And that's a lovely story, which unfortunately I don't have time to tell you. And in that case, they expand the laser beam using a telescope so that its width is several meters. So even when it goes all the way to the moon, the width only becomes a few kilometers. And that way you're not wasting the light. Okay. That was a small digression. Now what I'm going to do is, I'm going to try and justify Huygens' principle. Okay. So now someone gives you a slit. And what Huygens tells you is spherical waves come from each portion of that slit. Now we are not going to appeal to Huygens. We are going to say, whatever is in the slit, we are going to think of as a superposition of number of Gaussian wave packets. And if you superpose large number of Gaussian wave packets, which are fairly close to each other, you will get a more or less uniform illumination on this slit. Of course, you will not get a sharp edge of the slit because the Gaussian does not have a sharp edge. But you would have created a reasonable approximation to a uniformly illuminated slit. So now you make a number of small, narrow Gaussians, much less than the width of the slit. Then each one of them gives you a spherical wave. And right from the beginning, we have been saying that if you have one solution of the wave equation, you can superpose. So our Gaussian beam was one solution. We are superposing many of them. And what are we getting? We are getting a spherical wave originating from here, another one originating from here, another originating from here, and so on. And we are adding them up on this plane. So remember, this is what is called Huygens' principle. I do not want to call it Huygens' construction. Okay? Huygens' construction, you essentially picked up only this point. I mean, if you were interested in the ray from here, you picked up this point. Whereas now we know that whatever is coming from here has some influence at all points. So that is what is called Huygens' principle in optics textbooks. It's not very fair because Huygens never talked of interference or phase or anything like that. It should really be called the Fresnel Huygens principle. Because the person who did the mathematics that we've just talked about and much more is Fresnel. And that's why almost everything in this field is named after Fresnel. Okay. But I thought it was worthwhile taking you through this argument so that you appreciate that what you were told in school about Huygens' principle, number one, is not a complete lie. And secondly, you don't need something completely mysterious like secondary waves originating from a point, which is hard to justify. You can justify all this purely from superposing plane waves. Of course, it's a long argument. We superpose plane waves to get a Gaussian beam. And now we are superposing these Gaussian beams to get any kind of slit that you want. Right? So actually, we also recognize the limitations of the Huygens way of doing things. Namely that you purely as a mathematical device, you can think of secondary waves emanating from here. But this is a very peculiar way of solving the slit. It's as if we don't have any slit at all. We create a wave packet which is 0 here and here. And because it's 0 and here, we say, well, we are going to put a slit here, a metal piece here, and a metal piece here. And now we have solved that problem. Okay. Little unsatisfactory, but that's the best one can do to justify Huygens' principle based on superposition of these waves. A deeper insight into diffraction has to go beyond Huygens principle, and we will come to it toward the end of this lecture. And actually, the end of this lecture, as I said, could well be beyond 11:30, right? Okay. So now I want to, since we have at least approximately justified Huygens principle, let us check Huygens principle, whether it gives sensible answers in two cases. The first case I call zero slits. Okay. What do you mean by zero slits? There is no slit. You just have a plane wave, e to the I kx. In fact, the ky could be zero, so it's just e to the I kx, which means on this plane, the phase is a constant. And the phase of the electric field is a constant. Now I want to know what happens at P. Now for a single plane wave, from electromagnetic theory, you already know the answer. The answer is, if the phase here is 0 at x equal to 0, the phase here will be e to the I kx, it will be kx, and the intensity will be the same. Right? So Huygens principle should give us this answer, that if I sit at P, I add up all the secondary waves coming from this entire plane, I should simply get e to the I kx, nothing else. So that's the question I'm asking here, the zero slit case. And actually, we will see that this calculation will help us to calibrate Huygens principle. Huygens simply told you that there is a wave originating from here and coming here, right? He'll tell you what the strength of the wave was, etc. So we will learn all that, because in this case we already know the answer. So the wave coming from here will have a phase which is different from the wave coming from here. This is the shortest path. This is slightly longer. Geometrically speaking, the extra length is given by this. Yeah, that's why I drew the circle. And you can do a little algebra to find out what is this length. R is root of x square plus y square. Pull out x square to the power of half, so that becomes x. Then you get 1 plus y squared by x squared to the power of half. This is actually, this is still exact, but then it's approximate if you use the binomial theorem, right? You will get y square 1 plus some epsilon to the power of half is 1 plus half epsilon, right? So when you do that, you get x. So r is equal to x plus an extra piece which is proportional to x squared. Okay, the extra piece is x squared divided by y squared divided by 2x. And many of you may have seen this. It's a theorem in geometry. There's a simple experiment called spherometer where you measure the deviation between a sphere and a plane. So this y squared by 2x is the approximation we are going to give for this extra phase. So what do we have at the bottom? Right? We have pulled out the kx term. And now, of course, different parts of this wavefront are going to have different values of y. So we have to integrate. So what Huygens is telling us is, if you want to find out what is happening at P, pull out e to the I kx. So you already got the answer to some extent. But then you have this integral. And now, again, we are encountering an integral where you have the integration variable, this time it's y. And we are encountering the square of it here. So it's not that easy to do this integral. It's called the Fresnel integral, naturally. Right? So we're going to study that. So we take all contributions. So this is what is called Huygens principle, not Huygens construction. Huygens construction takes only one contribution from O, but now we take all contributions. And what is going to be the strength of the secondary wave? So e to the ikr. So the phase of the secondary wave is in, we are making a kind of paraxial approximation, right? That y is small compared to x. So it's y squared by 2x. But it's proportional to. We must fix the factor of proportionality in such a way that we get the correct answer. So this whole thing should end up being 1. After you've pulled out e to the I kx, everything else should be 1. So now we have to face it, no? So the next couple of transparencies will be somewhat algebraic, but I will try and give you a feel for what is going on. So here's this integral. You can take it from minus infinity to plus infinity. Now, of course, you may say that is violating the paraxial approximation. Okay, because y was supposed to be small compared to x. We'll come back to the justification for that. Now, as far as if you take it over the infinite range, of course, this integral has some parameters like k and x, but you can easily get rid of them. You define a variable u, which is just u square is ky square by x. So u is root of k by x into y. So then you get u squared, and to compensate that root of k of x, you put root of x by k outside. So really, this is the integral which we should be studying. Incidentally, this is also interesting, right? We'll come back to this. The integral has a value root of x. Now, just to remind you, we said that, so if the integral has a value proportional to root of x, this proportionality factor had better have a 1 over square root of x, right? So just remember that. We'll come back to it later. Now, this integral, if you take it all the way from minus infinity to infinity, can be done. And again, it's just square root of 2 pi into I. I is important. So it's actually square root of I, which is interesting. I is a complex number with a phase of 90 degrees. The square root has a phase of 45 degrees, which really means that this integral has both a real part and an imaginary part. Now we are interested in the value of the integral over the infinite range because we are interested in making sure that this kind of, I'm calling it Huygens approach, but really Fresnel approach, will give you the correct answer just for a plane wave without any slits. For that, you only need the definite integral. But suppose someone, again to go back a little bit, suppose someone, you're still sitting here and someone takes a metal piece and gradually starts moving it down from the top. So you will have an integral from minus infinity, but it will stop at some point. And of course, now we'll be discussing diffraction by a straight edge, right? Because this is only 1/2 of a slit. That's why I called it half a slit. Now, either you can fix half of the slit and move this point up and down, or you can keep this point fixed and move the slit down. That's what we will do. So moving the slit down means changing the upper limit of the integral. So if you want to understand the integral, now you may say, look, you're taking an integral from 0, why not from minus infinity? We'll take care of that, don't worry. What does the integrand look like? Cos of, we all know the plot of cos of x, but what is cos of u squared by 2? Well, basically goes up and down between -1 and +1. But obviously, this periodicity is going to shrink because successive zeros will occur when u squared by 2 crosses multiples of pi. Actually, odd multiples of pi by 2 in the case of cos. And now you notice that there's a heavy cancellation of the integral for large values of here as well as here. So most of the contribution of the integral comes in this range. So that is the justification for taking, so in practice, only fairly small values of y are important. In fact, this is roughly -2 to +2 or something like that. And the same is true for the imaginary part, S of v. So all we are saying is exponential I u squared by 2 is cos of u squared by 2 plus I sine u squared by 2. This will look like this. Okay. And as I said, if we understand this integral with a finite limit, we would have understood diffraction by a single slit. But let's first look at the experiment. And historically, a contemporary of Newton, an Italian priest called Grimaldi, did very careful experiments, in fact, darkening a room, letting in sunlight through a small hole, and studying the shadow of sharp objects at greater and greater distances. Okay, and you may ask, why was he doing all this? What was his profession? He was a Jesuit priest. Okay, well, Jesuit priests have contributed a lot. Gregor Mendel gave us the laws of heredity, and Grimaldi gave us, and he saw all these features, except because he was using sunlight, these features depend on wavelength. Okay, so he noticed that yes, you get something which is white, but then the next one is colored because you have different colors in sunlight. He was able to see 2 or 3 of these oscillations. This graph has been superposed on the picture. It shows you actually, if you use monochromatic light, you have many, many more oscillations. Okay, so this is the diffraction pattern of the single slit, which we should try to understand. And notice these are not equally spaced. Okay, and this is what Fresnel was able to explain using his integrals, and that's what we will try to do. Okay, but before that, well, yes. So what we really want is a plot of C and a plot of S, and then C plus IS as a complex number, as a function of the upper limit. Now, the way I made this plot, which is also the way that Mr. Cornu made the plot, except that he didn't have a computer, is approximate the integral by a sum. So e to the I u squared by 2. If u is 0, it's 1. Okay. So of course it gets multiplied by delta u, right? Because you're approximating. So draw a small vector of length delta u, which is the complex number 1. Then as u squared keeps increasing, the phase of this complex number keeps increasing. So for example, at this point, u squared by 2 is equal to pi by 2. So u is the square root of pi, about 1.77. Right? And now notice, because of u squared, the phase of this complex number increases more and more rapidly. Right? We saw that the oscillations of both C and S become more and more. So you get this beautiful spiral. And the same point which I made by looking at the 2 curves can also be made by looking at this. Most of the contribution is, say, coming from here to here. Right? A lot of cancellation near the 2 limits. And this is the principle which we mentioned, in fact, at the beginning of our discussion of ray optics, because some of you were impatient and you wanted to know how can you justify the rule of least time. Right? And I told you at that time that it's not really least time, it is stationary phase, stationary number of wavelengths. And now you can see the function u squared is stationary at u equal to 0, which is why you get, it's not changing very rapidly, and that's why you get this whole contribution. We saw that in the previous curve also. No? Sine of u squared and cos of u squared were changing slowly near the origin and changing much more rapidly as you went away from the origin. So this Cornu spiral actually, apart from teaching us about single slit diffraction, which we'll talk about, will also tell us more generally how the stationary phase principle works, and therefore how ray optics and the principle of least time emerge from wave optics. So that's why it's worth studying this spiral. Okay. Now, small digression. This straight edge diffraction of radio waves was actually put to use in astronomy, and I'd like to touch upon this before we go back to Cornu spiral. So this graph was taken at a radio telescope in Australia in the year 1962 by a big team of astronomers. There was a mysterious object emitting radio waves no one had any idea what is the corresponding object in, say, the visible region of the spectrum. And of course, optical astronomers were quite prepared to look for it. But for that, you need a very accurate position of this object. Okay, you need an accurate position so that when the astronomer points his telescope, he'll see thousands of objects. He can pick out the one which is the source of the radio waves. Okay? Now, unfortunately, radio telescopes have a very poor resolving power, and we'll come to that simply because the wavelength is long. But what these people did is they realized that the moon is going to pass in front of this radio source. By the way, the moon moves relative to the stars. We all know that in the Indian tradition, the moon visits 27 stars during a month. But fortunately, the moon also visited this object called 3C273, this mystery object, which was only known as a source of radio waves. And now, if there had been no straight edge diffraction, you would have had a sharp step. So, immersion is when the intensity goes down. Immersion is when it comes out. So, by finding the accurate time of the step and finding where the moon was at that time, you get an accurate position of the source. But actually, you get more information, right? Each point on the source will give you a straight edge pattern. Now, the fact that it agrees with the straight edge pattern of a point source tells you that the object is very, very small in radio waves, which you could not have guessed just by studying with a simple radio telescope. So this was really a great discovery. And then people went and pointed their telescopes, and they discovered a very unique object, which is very bright, very far away, and is called a quasar, a black hole at the center of a galaxy, etc., etc. Again, a piece of astronomy that unfortunately I can't tell you more about. But what I can tell you, and being a member of NCRA and part of the TIFR family, it's my duty to tell you that inspired by this, Professor Govind Swarup decided that whatever technique the Australians used should be used for much weaker sources. And you could collect them in large numbers, and the weaker sources are very far away, and thereby you could say something about cosmology. And he came up with a concept, and he was able to build it with the help of a team of engineers and young astronomers who were his research students. So they studied diffraction of radio waves at 90 centimeters by the edge of the moon, and they found the presence and the positions and the structure of hundreds of radio sources. In this case, they didn't even look for moon covering up a known radio source. They simply used the telescope to follow the edge of the moon, so the telescope had to rotate every day, so long as the moon was up. So Govind used to have this joke that we were professional lunatics because we followed the moon, right? And here's a picture of this magnificent instrument, 500 meters long, 30 meters wide, and able to follow the edge of the moon. And of course, once it was built, it was used for many other purposes, and gave rise to the same group went ahead and built GMRT. That's something I told you in the very first lecture. Okay. So this is straight edge diffraction. Now, maybe we'll go back to Cornu spiral and see how we understand this. So first, suppose that slit, which is covering up the incoming wave, is very far up. So you get the definite integral. Definite integral from minus infinity up to plus infinity. And that is this vector, which I told you is proportional to 1 plus I into root of pi. So that's what it is. But now suppose we cut off the integral at various limits. So suppose we push the slit so that it covers up even u equal to 0. So that means you are deep into the shadow. So in the shadow region, this vector, so this is the tip of the vector, which is the upper limit of the integral, which will now we'll have to wind it back and bring it somewhere here. So the intensity in the shadow region is very small, but as you come out of the shadow region, starts getting larger and larger. Of course, the phase also keeps changing a little bit. Right? And when is the intensity maximum? Not at the edge of the shadow. Not at, this is the geometric shadow, u equal to 0. Intensity is maximum somewhere here, right? you can just keep track of the length of this vector. Then it has a minimum but not zero. Again, a maximum. And these oscillations become weaker and weaker and also closer and closer spaced. So that's how the study of the Fresnel integrals and Cornu spiral explains straight edge diffraction, explains this pattern.
Sir, I would just like you to revisit that that one assumption that you've shown, that the strength of the secondary wavelet from a point x comma y is had that a particular function dependent on r, right? I just want you to revisit how you assume that.
Okay. It's just geometry actually. So let's go back to it. But maybe I went through it a bit too fast. So share screen. Okay, so let's define everything. We have this incoming wave. We have a point P where we are trying to calculate the total effect of this incoming wave. First of all, without any slit. And there is a point O, which is the perpendicular from P, which is the nearest point also. And that is also taken as y equal to 0. So y is a coordinate on the wave front. And the distance increases as y increases in either direction. That's clear even from this formula. Square root of x squared plus y squared. Now geometrically, you can see that r is greater than x. So if I draw this circle, up to here is r, and this extra bit is the excess over x. Sorry, up to here is x. Same radius, circle of radius x. So it's this extra bit which I'm saying is proportional to y squared. It's y squared over 2x. So the phase is kr is straightforward. No, it's just r divided by lambda into 2 pi. And that in this paraxial approximation is x plus y squared by 2x. And the justification for that using binomial theorem is given here. So does that answer the question?
Sir, I just wanted to bring your attention to this word strength. Like, so what do you mean strength?
Okay. So this is the complex strength. It's the electric field, not the intensity. In fact, the intensity, so that's why I said proportional to. So this is the phase part. Sorry. So I actually, I should have said maybe, yeah. If I removed this word strength, it would have simply said the secondary wave is proportional to this. This part gives you the phase. But if you simply put this without any factor in front, you will get this formula, right?
Right.
And that will not be e raised to ikx unless I put the correct proportionality. See, this integral is not 1. Okay. This integral is something, is actually square root of 2 pi into I or something like that. Into root of x by k. So the reciprocal of that factor has to be plugged in. And that is the amplitude of the secondary wave. So yes, actually, I'm happy you made this point. So strength is not what we really meant. This is just the phase factor, and the amplitude factor is to be obtained by evaluating the Fresnel integral.
Right.
Which we will do. I exactly stopped at that point.
Right.
Okay. 3 participants raised their hand.
Yes, Manu can go next.
Hello.
Yes.
Sir, can you explain how the principle of least time came from the Cornu spiral again?
No, Cornu spiral is for a very specific problem, namely diffraction by a straight edge. But what it tells you is that, so I would rather say that Cornu spiral illustrates the principle of stationary phase. Okay. So we have an integral. Integral was exponential I into u squared by 2. So the phase part was u squared by 2. And u is really proportional to y. Now u squared by 2 has actually a minimum at u equal to 0. So let me go to in fact the previous, I think the previous one will illustrate that. Yeah. So the integrand is cos of u squared by 2 plus sine of u squared by 2. Now you notice that these functions vary slowly near u equal to 0. And the reason why it's varying slowly is that u squared itself is varying slowly. If you draw a graph of u squared, it's a parabola. And near the bottom of the parabola, the tangent is horizontal, it's varying slowly. So that's why cos of u squared and sine of u squared are varying slowly. And then if you go up in the parabola, it's varying very rapidly and all these cancel out. When you do the integrals, they tend to cancellation. And you can see the cancellation for the real part and imaginary part in this graph. And in Cornu spiral, you see the cancellation in the complex plane. That the curve keeps on winding round and round. It doesn't go anywhere. Well, it does ultimately go to the infinite value. So I would rather say that Cornu spiral is a way of depicting Fresnel integrals. And the fact that the main contribution to Fresnel integrals comes near u equal to 0 is an illustration of the principle of stationary phase. Now you generalize that principle and say the phase along any path depends on the number of wavelengths. And if that is the minimum, that path is going to be very important. That's the argument.
Anand has a question.
Hello, sir. I like in the problems, right? There was this uncertainty relation between the spread of y and theta on the x equals 0 plane. So I couldn't help but notice this was like very similar to like Heisenberg's uncertainty principle, and I could sort of reason that if the wavelength was the de Broglie wavelength, it would resemble it. But is it reasonable to think of a particle as a wave, like kind of radiated from a Gaussian source? And if not, is there some other generalization from which both of these things come?
Well, if you're dealing with very weak source, single photons, then I think your picture is correct, right? The momentum of that is h over lambda, and it has a wave function because it's a quantum mechanical particle, so it has a kind of wave function, or even a single electron. Let us say. So I think you're thinking along the right lines, and of course, to make the statement more precise, one should phrase it in the language of quantum mechanics, and by that I don't mean just de Broglie relation, right? The full quantum mechanics, where you have wave functions and some equation and also some various rules from which you calculate observed properties from wave functions. But all of them have their parallels in wave optics. That's kind of interesting. So yes, I would say broadly the answer is yes, but please don't be satisfied with that. I can help you later to pursue that analogy and make it precise.
And sir, I also just had like another question. Right now we're like considering it to have been distributed as a Gaussian, and from there I guess you can use like that integral for like the error function gives like the root of 2 pi by alpha, and it comes like that. But does it like generalize to other kinds of probability distributions as well, which peak in the middle and
completely? So the only thing which will change is you'll replace the Gaussian function by some other function, right? Let me see. So okay, so take this away, put some other function. So this becomes what is called the theory of Fourier transforms. Okay. Some function of theta multiplied by exponential I theta into y. I mean, all this k and all can be absorbed. So it completely generalizes, and you have to just study the theory of Fourier transforms. And there are nice tables, and for various functions you can find the Fourier transforms. If you can't find it, you can find it on the computer. So there's nothing specific. Gaussian is completely chosen for convenience. As I said, it's a bonus that laser beams tend to look Gaussian. But I just chose it because it's it's something where you guys, without believing something that I just tell you, will be able to verify it for yourself. If you know more Fourier transform theory, you can do more.
Thank you, sir.
I guess there are no more questions. So.
So in any case, what's going to happen is that we are resuming at 11:30, And we will have time. I will go over the remaining slides slowly, and we'll have time for questions. So people will just have to wait to that time. So I don't mind taking the break now, but tell me if there is something pending, like maybe someone from YouTube, I don't know. I've gone back to one of the earlier slides where we said that the contribution from a point y on this wavefront to a point P in front of the wavefront is going to be an integral over y, and you will have exponential ikx, which is this distance, but inside the integral something which depends on y, which is this phase corresponding to this extra distance. Now we said proportional to, but we know from our understanding of plane waves that this factor should really be 1. So we should choose the proportionality factor to cancel this integral. Okay. And since I told you what the value of the integral was, right, it's not difficult to choose proportionality factor. So if you do the algebra, which is not very difficult, with the proper constant, we get square root of k divided by 2 pi ix exponential iky square into 2x. So this has to be multiplied by the electric field at any point y on the wavefront and integrated with respect to y, and that will give you the electric field at the point P, which is a distance x in front of the wavefront. Okay. Incidentally, a small point of dimensional analysis, you know that k has dimensions of inverse length. So you have 2 lengths in the denominator, you take the square root, you have 1 length, and then when you multiply by dy, that goes away, and therefore whatever, if you start with electric field, you end up with electric field. But this 1 over square root of x, of course, came out from an algebra. I also want to tell you that it's quite natural. And here I want to point out that we have throughout been working in y and x, ignoring z. And I said it's 2 dimensions. It doesn't mean that we are working in a flat region. We're working in 3-dimensional space, but nothing depends on z. So if I draw a circle, it's really a cylinder. If I put a point, it's really a line. If I draw an obstacle, which is a straight line, it's really a screen. Okay. But I want to take the story of diffraction a little further. Now, Huygens historically believed in an ether, which was full of small particles and so on. And for him, there was no difficulty in thinking that each particle could act as a source of waves. But later on, when simplified versions of this were put in textbooks, people said waves emanate from empty region inside a slit and so on. He never said any such thing, right? In fact, I think C.V. Raman, quite late in his life, in 1959, decided that people are misrepresenting Huygens too much. He wrote a nice article, essentially a review of that book and later developments. And in fact, I'll put it up in Moodle. It's a very powerfully written piece. Now, the justification that we have seen came in the work of Fresnel, but only as an approximation. And then Kirchhoff, whose name you would have heard in connection with other subjects like heat and current electricity, tried to improve Fresnel's justification. But he was still making some fairly drastic approximations. And at this level, it's what is called Fourier optics. I explained that Fourier transforms are essentially integral of any function with e to the I times y times k or something like that. So whatever we've been talking so far is a kind of Fourier optics. And if someone wants to pursue this line of thought further, there are nice books on Fourier optics and so on. However, as I told you, Huygens principle is approximate. So what is the truth, right? And we may have an exact theory which is so complicated that we cannot implement it, but at least it's good to know that there is such a theory. Right? Either you have to go to a very advanced book like Born and Wolf to learn about what is called the rigorous theory of refraction. But very much to your surprise, it's also there in an undergraduate text, which is the Feynman Lectures, Volume 1. Now, volume 2 of Feynman lectures is electromagnetic theory. So what business does he have discussing optics in these chapters, 9 chapters, I think, of volume 1? Right? And the answer is, he has a simplified version of electromagnetic theory, but actually which contains all of electromagnetic theory, but not giving Maxwell's equation, wave equation, nothing of the kind. He just tells you that if I move a charge in a certain way, what electric field and magnetic field will it produce at all times, at all distances. So it includes Coulomb's law, includes radiation, includes everything. Of course, that you have to accept. But if you can accept Maxwell's equations, you can accept this. Okay. And then the second thing is that, of course, you have to know what this electric field and magnetic field will do to another charge sitting somewhere else. So he writes down that. So he just writes down these two things. And the entire discussion of optics takes place based on these two things. And the advantage of that is you never have to unlearn it, because the formula he gives actually comes from Maxwell's equation. So, and the principle he uses in discussing optics is that electromagnetic waves have to come from sources, that is oscillating currents. If you're interested in a single frequency, currents which oscillate at some frequency. So a diffraction problem is really a physics problem. You have put maybe some screen, some pieces of glass, and so on. Then you have some source. So there is some current in the source. That has to be given to you. If you don't tell me what the original source of light is, I can't solve a diffraction problem. But once you give the source, and once you give all the objects which are lying around on which the electromagnetic field from this source falls, what happens? If current falls on a metal, the electric field drives some, if the electromagnetic wave falls on a metal, the electric field drives currents in the metal. It's true also that even if it falls on glass, glass is of course an insulator, so it can't take a DC current. But if you have an alternating electric field, then the electrons and the nuclei in every atom of that glass will get separated by the electric field, and then half a cycle later, they'll get separated in the opposite direction. So these are induced currents, or you can call them dipoles, since you are talking of separation of positive and negative charges, which happen in all these objects. And then these in turn become sources. They also start radiating. So you simply say that the full solution of the problem, you will take the field of the original source, and you will take a field of all. These are physical secondary sources, not to be confused with Huygens secondary sources, which are fictitious. Okay, these sources reside in material objects, screens, lenses, whatever it is, right? And believe it or not, he develops all of optics from this viewpoint. And he, it's not original with him. It was a very profound remark about diffraction, which was made in the early 20th century. Okay, so let me actually come to that and come back here. Yeah. So let's just think of a problem. Okay, I can actually go to the slideshow mode. No, it looks like I cannot go to the slideshow once I hope this is clear enough. We'll just continue with this. Yeah. So this is this theorem, which was discovered by these gentlemen quite late, if you think about it, in the progress of optics, right? And the simplest example would be an incident wave falling on a flat metal plate, infinite plate, no holes, nothing. It's a mirror. And so you get a reflected wave. The usual explanation we give is that the metal plate reflects this wave, and therefore behind the metal plate there's nothing. But suppose you take the point of view which I just explained to you, and the point of view which Feynman makes the basis of his discussion with optics. Then you have a source, and that creates a wave, and that wave fills the whole of space. Okay. Now, what about all these metal? They are also some other charges. So maybe they will start oscillating, and they will also radiate some other waves. So suppose you now think of currents in the metal sheet. Okay. Now I have currents in this metal sheet. They are produced by the incident wave, electric field of the incident wave. But once you put currents in a metal sheet like this, is there any reason why it would not radiate in both directions? It will, right? So these currents actually go in both directions. Okay. In addition, the incident wave also goes to the region behind the sheet, but the two cancel. They cancel, and that's why you get zero electric field here. So, and a reflected wave here. So this is called the extinction argument, and it's not an argument. It's an argument for the simple case, but it's a theorem. And they proved it in general. Ewald in particular was concerned with X-rays propagating in crystals, but also optics. And this is something we are never told in optics. Right? But you can see from the logic I've given you that this is the most rigorous way to think about optics. So we'll come back here. So if you want to go beyond Huygens principle and all this mathematics of Kirchhoff and so on, right? This is the way to do it. And of course, it's not original with Feynman. It was done by Sommerfeld. It was in various people, right? So basically it says do all currents. Now, let's say we make a hole. Now these currents are going to change. Now the original currents cancelled the electric field behind the metal sheet. But the modified currents cannot do that. So the modified currents are responsible for the diffracted wave. So this is a rigorous theory. Now, interestingly, as you know, in everything, English and French are rivals. So there was Fresnel's theory, which said integrate over the whole wavefront. So Young, at slightly earlier, in fact, said, I don't understand all these waves coming out from inside the slit. I should be able to explain everything by two waves coming from the edge of the slit. Now, it turns out this is also an approximation. And it's also very interesting. I'm not giving you the details. Maybe I can set up some problem based on that. If you take the integral as given by Fresnel, and if you integrate it by parts, you will get contributions from the two boundaries, which is the edges. So mathematically, the edge wave theory of Young and the theory of Fresnel are both approximations. And so Young, if you ask, how did Young explain the single slit diffraction? He said, I have this plane wave. Whatever goes above the slit continues. So I have a plane wave here. But then I have a cylindrical wave coming out from this edge. And if I look at the difference between a circle and a plane, we have already seen that difference is proportional to y squared. So therefore, your interference pattern here will be the integral of a function which is proportional to y squared. So the edge wave is able to explain it. Of course, to explain the intensity and why the intensity is very low here, you have to say that the intensity of the edge wave is not uniform on this circle. It falls off as you go away from here. Now, as I said, this is an approximate theory. Now, Sommerfeld actually gave a theory for this problem, which is exact in the sense the only thing he uses is Maxwell's equations and the correct boundary condition on this metal plate. Okay. Now, that theory shows that the edge wave theory actually is not completely wrong. There are some terms like that. But the approximation of edge waves fascinated Raman. So he followed up on the work of Sommerfeld and looked at different kinds of apertures for which you can't give a rigorous solution. One of his fine students, whose name we have encountered, Ramachandran, in connection with crystallography. When he did his PhD, he worked on this edge wave theory. It's called a geometric theory of diffraction. That theory was somewhat intuitive, as done by Raman and Ramachandran, and even earlier by K.S. Krishnan. But a person called Keller put it on a rigorous mathematical basis. Okay. So now, why don't people do this rigorous theory? Right? And the answer is, if you want to know what is happening on a piece of metal, it's not enough to take only the incident wave. There are other pieces of metal which are also radiating, and they will affect this piece of metal. Right? So your solution has to be self-consistent. You assume some currents sitting on pieces of metal, whatever they are. Those currents will tell you what the electric field is at other places, okay, including other pieces of metal. And then will this agree with the electric field you originally assumed? So to start with, assume some electric field on each piece of the metal, right? And the metal could be an aeroplane. Now, why would you want to calculate diffraction by an aeroplane? Because in a military application, you send an electromagnetic wave from a radar set, it hits the aeroplane, and then some field comes back to you. So you would like to solve that problem, and not even Sommerfeld is going to solve that problem for you. You need a computer code. And the way that computer code would work is assume some reasonable distribution of sources. At least one of the codes will work that way on the metals or other things, and see if it is self-consistent. So the sources will produce field at other points. Is that the field which you originally assumed? If not, you modify it and so on. So this innocent looking equation actually tells you that. And this is more or less where I'm going to end. Okay. So let me explain. You have an incident wave. But the electric field at any point is not just the incident wave. It's so take any point R dash. So electric field is at R. Now I may have some piece of metal sitting at R dash. It need not be metal. It can be glass or anything like that. Now that piece sees the total electric field E due to all other pieces. So E is equal to incident plus this E. But this is sitting at R dash, and it radiates something, and that formula is given by some G of R dash. And that contribution at R also has to be taken into account. So this idea of self-consistency, which I explained to you in words, if you formulate it in equations, you can see it's like this. So for example, one way to make a guess for E, plug it in here, calculate this, you will find you get some different E on the left-hand side. Then you maybe improve it. Or there are other ways of solving such equations. And it turns out that this kind of equation is the fundamental equation of scattering theory. And this G is essentially the wave which propagates from R prime to R, keeping in mind that some unit electric field is exciting the object which is sitting at R prime. So it's quite easy to say in words, as people say, easily said, not so easily done. But I thought, since we have learned so many rough and ready approximate things, Huygens principle to start with, then improved version of Huygens principle using paraxial optics and some oscillatory integrals and so on, I thought it would be nice for you to see the whole story, even if the story is only in outline. Right. So really, I've come back to where we began this lecture on wave optics. What is the G of R dash? I have something sitting at R dash. It's an oscillating current. And of course, what that current is depends on the properties of, is it a metal? Is it, a dielectric? And if you know that, in principle, you can do it. So thanks. This is the amount of material I wanted to cover in this final installment of wave optics, and also the final installment of the course of lectures. Like all TV serials, the last installment is allowed to be a little longer so that you can tell the story a little more completely. Of course, the story is not over by any means, right? And as I indicated to you, we would try to follow up in a different way with maybe not the whole group of tutors, not the whole group of students, but I will be there. How we are going to do this will be decided based on a questionnaire which we will send out. And now let me take questions on this part of the lecture. Yes?
Sir, so I wanted to know how in the extinction argument, how did the incident wave get cancelled off to zero? I didn't get that part.
Okay. Let's go back. All right. So to actually prove it as a theorem, you have to have a formula for what a current here will radiate. In this case, I can give you a simple argument that for a perfect mirror with no absorption, the strength of the reflected wave equals the strength of the incident wave. Okay. You agree? I mean, it's a perfect mirror.
Yeah.
And then if you have, but we have this insight now that the reflected wave is produced by these currents. And when you have currents in some plane, there's complete symmetry going in this direction and this direction. So the wave radiated by these currents will have the same strength as the reflected wave. So now we have one wave which is equal to the reflected wave, and one wave which is equal to the incident wave, which is the wave coming from here. Now we have a choice, right? If they don't interfere destructively, then you will even violate the law of conservation of energy, right? Because you will have incident wave, equal energy going back in the reflected wave, and more energy coming here. So for consistency, it must be that the wave radiated by these currents has extra phase of pi relative to the incident wave. It's equal to the incident wave, I've already justified. Now that pi comes from a detailed calculation. There are calculation of this object GRR, right? It's there in the Feynman lectures, by the way. And actually it gets much better than that. Since you raised this question, suppose this is not a metal sheet. Suppose the sheet of glass, dielectric. Then what Feynman proves is that the incident wave is still cancelled, and here you get a refracted wave, right? So that's very nice. Okay.
Thank you, sir.
So you have to do some work. It's not obvious. I mean, that's why it took till 1915 and these two extremely bright gentlemen to realize this fact, which is really a fact about basic optics.
Sir, in this same thing, how means the incident wave is just totally absent when it strikes the metal sheet. That means whatever the energy incident wave has, it is transmitted to the metal and their oscillations. So afterwards, one incident wave is converted to two reflected waves only. So this forward moving reflected wave or the new wave is interfering with which wave, because there is nothing to interfere with forward.
No. The viewpoint is that the electric field at any point is the sum of all currents, what is produced by all currents. So whatever currents are producing the incident wave have to produce an electric field here. And these currents also produce an electric field. So as I said, the viewpoint here is that basically we are dealing with a scattering problem. We have one source of an incident wave. We have various objects, which in turn can radiate. But that doesn't mean that the original thing has gone away. So whatever you see at any point is the sum total. So I agree, this is a somewhat unfamiliar point of view. But interestingly, it can explain reflection, refraction, everything. Yeah. And there I would, since I don't have the time, and also because I'm not Richard Feynman, I would strongly urge you to read that section. So all that we are using is the superposition of electric fields radiated by different sources, which is a fundamental property of Maxwell's equations because they are linear. Now, where you have to change your mindset is don't think of a metal sheet as, something with some given properties. Think of it as a set of atoms which also consist of charges, which can also oscillate. Now, interestingly, when you assemble a large number of them, they behave in this interesting way.
Sir, so if we change, suppose we change the shape of the sheet so that the incident wave and the reflected waves are not exactly parallel or completely superposing. So how can we explain that zero intensity forward again?
So these papers were very general. They proved the extinction theorem without making any restrictive assumption about the shape of these objects. So look, my purpose is to give you a glimpse of these developments, but definitely I think many of you may feel that you're already doing enough hard work by doing Gaussian integrals and so on. But if you, at least in simple cases where the material consists of slabs and so on, the Feynman lectures will tell you how you generate a refracted wave, how you generate. So it is independent of shape. I chose the simple geometry where it's pretty clear what is happening. Well, maybe I can give you a kind of analogy, may make it better.
Yes, sir.
If I put a charge, electrostatics now, and a metal sheet, then it induces another charge here, and the two charges cancel, so you don't see any field on this side. That's what's called electrostatic screening.
Yes,
But
sir.
electrostatic screening also applies even if this is not a flat plane, but it has some complicated shape, except you have to do a little more hard work to prove it. So if you like, it's something like a screening argument. But I mean, if you want a little more mathematics, I would say that the electrostatic screening is based on Laplace equation, and this extinction theorem is based on the wave equation. Yeah.
Okay, sir. Thank you, sir.
So you have been mentioning that Huygens principle is also sort of an approximation, but like I would like you to reiterate on that point. Like, isn't everything we've seen here like can be put into the Huygens principle of secondary wavelets?
No, because the Huygens, for example, whatever I told you in the last, I don't know, maybe half an hour or so, is based on scattered waves which have a physical origin. Right? They originate in charges, in matter, in metals, dielectrics, and so on. Whereas the Huygens principle asks you to believe that waves originate in empty space inside a slit. Now that we kind of justified by fairly elaborate arguments. If you use more mathematics of Fourier transforms, the same argument can be stated in a more concise fashion. But in order to get that principle, you have to make certain approximations like paraxial. And as I said, even the improved attempts to justify Huygens principle by Kirchhoff again had to make approximations. So really, if you're interested in being physically and mathematically rigorous, you should forget Huygens and go to the rigorous theory of diffraction.
So my main question would be, is the rigorous theory the one based on Fourier transforms?
No, not necessarily. The rigorous theory is based on this equation.
Okay.
The Fourier transform is an approximate. So Fourier optics is also an approximation.
Okay.
The rigorous theory is based on this equation. Where this G will actually be more like spherical waves. Because if there's a source at R prime, G will be more. So this is a more rigorous theory.
So if we were talking about this theory in vacuum, where we didn't have like matter for electromagnetic waves to interact with, so that would still be consistent with Huygens construction, right?
It's consistent with, yes, but we don't need it.
Yeah.
Because from Maxwell's theory, plane wave is the simplest solution, right?
Yeah.
So then what you're basically saying is strike off this term. Easy incident. Yeah, it's a very powerful idea and unfortunately not emphasized. So I would urge those who are really interested to go to those chapters.
Thank you, sir.